The PLC scan cycle catches every beginner exactly once. The program runs. The inputs change. The output does something you did not expect. You spend 2 hours staring at a rung that looks correct, and the bug is not in the rung at all. The bug is in how the scan cycle works. Once you understand it, you stop getting trapped by it. This video covers the 3 phases of the scan cycle, the snapshot rule, and the timing reality of a real PLC. A PLC runs your program in a loop, called the scan cycle. The loop has 3 phases. Phase 1 is the input scan. The PLC reads every physical input, every button, every sensor, every switch. It stores a snapshot in a memory area called the input image. Phase 2 is program execution. The PLC runs your ladder logic from top to bottom, rung by rung, using the input image, not the live physical inputs. Phase 3 is the output scan. The PLC takes the resulting output image, also held in memory. It writes that out to the physical outputs, lights, motors, valves, indicators. Then the loop repeats. Read, run, write. Read, run, write. Forever. The PLC has been doing this loop quietly behind every machine in your factory. For years. Without anyone noticing it is even there. The thing that catches every beginner is the snapshot rule. During Phase 2, while your program is executing, the PLC is not looking at the physical inputs at all. It is looking at the snapshot taken during Phase 1. If a button is pressed and released during Phase 2, the program never sees it on this scan. It sees nothing change. On the next scan, Phase 1 runs again and captures the new state. But by then the button has been released, and the snapshot shows it as off. Fast events between scans are invisible to your program. The first time a beginner runs into this, it feels like the PLC is broken. It is not broken. It is doing exactly what it was designed to do. The trade-off is determinism. The PLC is predictable because it does not react to physical changes mid-execution. The next thing to understand is how long one scan actually takes. A small program on a basic PLC like a Siemens S7-1200 might complete a full scan in 1 to 5 milliseconds. A larger program on the same hardware might take 10 to 20. A complex program on a slower PLC could go up to 50 or 100 milliseconds. Modern industrial PLCs are usually well under 20. Allen Bradley compact logics and control logics sit around 2 to 10 milliseconds for typical programs. Mitsubishi Q-Series similar. Older Siemens S7-300 systems can be slower, 20 to 50 in some configurations. The scan time matters because anything happening faster than the scan, the PLC cannot see directly. A button bounce that lasts 5 milliseconds on a PLC with a 20 millisecond scan may be missed entirely, or seen as a single press, depending on when it lands. Most PLCs let you read the current scan time as a system variable. Check it on any program you write. It tells you how much headroom you have for additional logic. In practice, the scan cycle has 3 real consequences for your programs. The first is that you can never assume an input change happens at any specific moment. You can only assume that what was true at the start of the most recent scan is what the program sees. The second is that program output changes propagate within a single scan. If rung 1 turns on output Q1 and rung 5 reads Q1, rung 5 sees the change immediately. Both rungs use the live output image during execution. But anything that depends on a physical input change cannot be seen until the next Phase 1. The third is that for things faster than the scan, you need special hardware. Pulse catch inputs, high-speed counters, or interrupt-driven blocks, not regular ladder logic. These features exist on every modern PLC, but they are configured separately from your normal ladder, often outside the scan cycle entirely. This shows up daily in 3 places. The first is debouncing buttons. A real industrial push-button bounces for a few milliseconds when pressed. On most scan rates the bounce is averaged out, but on fast scans it appears as multiple presses. Hence the timer-based debounce patterns you see in industrial code. Usually a TON timer with a 50 millisecond preset that filters short bursts. The second is detecting edges. To detect that an input just went from off to on, not that it is on, you need a one-shot pattern. It compares the current scan state against the previous one. Every PLC vendor has a built-in one-shot or rising edge instruction for this, but the underlying logic is just a comparison against the last scan's value. The third is reading encoders, or counting fast pulses. A typical incremental encoder generates pulses faster than any reasonable scan can read. For anything faster than the scan, you need a dedicated high-speed counter peripheral that latches counts and hardware between phases. Scan time matters more in some industries than others. Food and beverage packaging usually runs scan times in the 5 to 10 millisecond range, fast enough for conveyor and labeling. Automotive body shops run faster, 2 to 5 milliseconds, because the welding and material handling robots demand it. Power generation tends to be slower, 10 to 50 milliseconds, because the underlying physics is slower. Water treatment is the slowest, often 50 to 200 milliseconds, because pumps and valves change state over seconds anyway. When you write a program, the first question to ask is what scan rate the machine needs. The second is how much headroom you have in your current scan time. The third is whether your slow code is forcing the whole scan to wait, a common cause of unexpected jitter. Run a scan cycle yourself at plcsimulationsoftware.com. The simulator visualizes every phase as it runs, so you can see exactly when the snapshot is taken and when the outputs are written. Next video covers the 7 most common PLC programming mistakes and how to spot them in a code review before they cause downtime. See you there.